This section 2.2 of the three sections, I think is straightforward, but if there's anything that will trip you up, it'll probably be this information right here that I've noticed in whatever past 15, 16 years of teaching this class. And people get hung up with it because here the question is to be able to find the determinant by using row reduction, like row echelon form. And so you're thinking in your mind how you did row echelon form, how you reduced the matrix to try to build a triangular matrix. That was the idea. Here we want to try to make the matrix become triangular so that I can multiply the entries along the main diagonal and get the determinant. So I can reduce the matrix. In the process of reducing, you got to be very careful because there are three things here. If you have a matrix and you want to take out a number that's in a row, factor it out, you put that number in the front of the determinant. So here, if B is the matrix that results from a single row or a column of A being multiplied by a scalar K, then the determinant of B is K times that determinant of A. Look at the example, matrix A and matrix B. Get that cursor, that arrow out the way. The only difference between matrix A and B is that matrix B has a factor of a -5 multiplied to row 1. If I didn't have that, then I have the same thing as matrix A. So the determinant for matrix B would be, notice that I can factor out a -5 here by looking for this determinant. So this is going to be -5 times what I have left is matrix A. So it's -5 times the determinant for matrix A. Right? In row echelon form, you would say, I'm going to divide, in reducing matrix B down, you would say, okay, I'm going to divide row 1 by -5. You'll say -1/5 times row 1. And it seems like you've canceled out, you've gotten rid of. But for the determinant, you factor that term out. You don't throw it away or you don't divide it out. So that's the one thing that's different, and you got to be very careful about that. So you got to separate in your mind solving a system using elementary row operations versus finding the determinant using elementary row operations. Here the notation somewhat changes. The second thing is that if you want to interchange rows, remember in row echelon form, you just interchange the row, right? But for the determinant, if you interchange rows, you negate the determinant. So you got to remember that. Those are only two things. The third aspect of it, if B is the matrix that results when two rows or two columns of A are interchanged, then the determinant is negated. The third aspect, there's no change. Here, if B is the matrix that results when the multiple of one row of A is added to another row of A, almost like how you would say the process back then for solving a system, you may have -2 times row 1 plus row 3. Here, what we're saying for the determinant is that the result does not change. No change in the determinant. So if B is the matrix that results when the multiple of one row of A is added to another row of A, then the determinant of A is the same thing as the determinant of B. So there's no change there. You only change the determinant. It's negated. If you interchange rows, you can interchange columns the same, and it's going to be negation to the determinant. Or if you have to factor out a common term in a particular row. If you have a 3 by 3 and you factor out a common term, if a common term is in all the rows, like if it's a 5 multiplied to everything in row 1, row 2, row 3, then you'll say 5 to the 3rd power times the determinant, right? But if it's just one row, you just take out that 1 5 times the determinant. I'm going to work a problem using this. And this is the craziest thing, because I'm telling you, if there's any problem that's missed on this exam, the last section, which I think is a lot of stuff, but it's just straightforward computation, everybody always gets that right. It's just when it comes down to finding the determinant by using row reduction form, that, man, it's something about factoring out that number, or the negation when you interchange rows. It just throws people off. Well, let's see. I'll work a problem, then I'll let you work a problem. Here's something neat, I think, before I get there. If a square matrix has a multiple of 2 rows or a multiple of 2 columns, you know, in reduced row echelon form, when you're reducing that matrix, if there's 2 rows that have a multiple, or 2 columns that have a multiple, you can get rid of one of those rows or columns by doing that reduced row echelon form, whereby you get all zeros in that reduction. So here, the theorem says that if you have a square matrix, and you notice that, like, look at this example for matrix A, row 3 is a multiple of row 2. So automatically here, this theorem says that the determinant is 0. Why is that? If I do row reduction by saying negative 2 times row 2 plus row 3, that would leave me with all zeros here, right? And computing that determinant, you got to multiply each cofactor by that 0. And so the result would be 0 for your determinant. The determinant of a square, diagonal, or triangular matrix, the product, we stated that above, is the product of the entries along the main diagonal. And so here, this is a diagonal matrix, and so the determinant is just 2 times 1/3 times 6, you just get 4. Okay, here's the problem. Evaluate the determinant of a given matrix by reducing the matrix to row echelon form. What I wanted to do here was just to put my steps in here so that you can see the flow of what we're trying to do. What we want to do is to be able to build an upper triangular matrix. So then whatever factor you have on the outside times the entries along the main diagonal gives you your determinant. But how to get there? Well, let's get that eraser out the way. So here, I noticed that in row 1, there was a common factor of a 3. So I factored it out. So it becomes 3 times the determinant. Remember, these slash marks represent determinant. So it's 3 times. I took out the factor of 3 from row number 1. And then the next thing I did was, I said, okay, I'm going to use this 1 to get a 0 where that negative 2 is at A31. So I said 2 times row 1 plus row 3. So that'll be a 0 here. So it'll be 2 times 2 is 4, plus 1 I get 5. Then 2 times negative 3 is negative 6, plus 5 I get negative 1. The next thing I did to build the triangular matrix is I interchange rows 2 and 3. You do that, you negate the determinant. So now I have a triangular matrix. So the determinant is that negative 3 times the 1 times the 5 times the negative 2, you get 30. You think you can do number 2 by yourself and get 5? Let's see. Let me give you a couple minutes on that. Okay, what I would probably do is interchange rows 1 and 2 first. There's going to be negative 1, 1, 2. 0, 3, 1, negative there, 2, 4. Then we use this 1 to get a 0 where that 3 is down there. So, you know, we're going to say negative 3 times row 1 plus row 3. There's no change to the determinant. This is equal, negative in front, 1, 1, 2, 0, 3, 1, this is 0, negative 3 and 2, negative 1, negative 6 and 4, negative 2. Now what I'm going to do is interchange rows 2 and 3. You don't have to, but I'm going to. So that becomes negative 1 times a negative. We'll just put a positive, right? So it becomes negative times that negative. So this is 1, 1, 2, 0, negative 1, negative 2, 0, 3, 1. And then you can use this negative 1 to your advantage to get a 0 here. So here we'll say 3 times row 2 plus row 3. Zero, 0 there. We get negative 6 plus 1 is negative 5. So we multiply, this is an upper triangular matrix, multiply the entries along the main diagonal. We get 5. Okay. Any questions there? What do you mean, fraction? Uh-huh. No, I did that second interchange because I was thinking along the diagonal I wanted a leading 1. And so I got a negative 1 there, and then I used that 1 to get a 0 below it. That's what I was thinking. Yep. Yes, sir, Daniel. Yes, sir. Because if look at a row, if there's a common factor in that row, you can factor it out. So I pulled out a 3 from row 1, I put it there, so that left row 1 is 1, 2, and negative 3. Okay, and that goes back up here to the property. It was that first one that said that if B is the matrix that results from a single row or a column of A being multiplied by the scalar K, then the determinant of B is equal to K times the determinant of A. And I gave an example here. This is the matrix A, the matrix B. The only difference is matrix B has a factor of negative 5 times row 1. So we take out, you can factor out that negative 5. Let me show you here. This determinant of A here would be 4 minus 6. We get negative 2. Look at the determinant of the B. The determinant of B. Since I know that there's a common factor of a negative 5, I'm going to say negative 5 times 1, 2, 3, and 4. So here, this is negative 5 times the 4 minus 6, which really was just negative 5 times the determinant of A, which is that negative 2 on the inside. So this is negative 5 times negative 2. We just get 10. So all we're saying is that if you notice that there's a common factor in a row, you can factor that number out. Don't throw that number away, multiply it times that determinant. Right? It could be a common factor in the column. You can take that common term out and multiply it times the determinant. Now here's what I've seen in the past what people would do, because they're still thinking row reduction in terms of the elementary row operations, and so I've seen people, they would say multiply on the outside of the matrix by negative 1/5. You're not doing that, right? We're finding the determinant, not solving the system. That's the difference, okay? And so I want to go right by here what this theorem says in terms of how I ought to operate. This axiom A, axiom B, axiom C. Okay. Well, thank you. Do well on the test on Wednesday, and if you have any questions, questions, just email or call, and whatever I can do, I'll try to help you out. Thank you.